Billions of years ago, long before humanity gazed up at the stars and wondered about our place in the cosmos, our corner of the Milky Way, this very region of space we call home, was a vastly different place, almost unrecognizable compared to what we observe today. Instead of the familiar sight of planets gracefully orbiting a radiant sun, there was a vast, cold, dark cloud of gas and dust, an immense structure stretching for light years, a cosmic ocean of raw materials. This cloud, which we now call the solar nebula, a name that hints at its future destiny, was primarily composed of hydrogen, the most abundant element in the universe, with a significant amount of helium. The second most abundant, and scattered throughout, were tiny grains of cosmic dust, specks of carbon, silicon, and iron, forged in the hearts of dying stars. These dust grains, though microscopic and seemingly insignificant on their own, were destined to become the seeds for future worlds, the building blocks of planets and asteroids. The solar nebula was, in essence, a stellar nursery, a cosmic cradle, holding within it all the raw materials necessary to create our sun, the star that would eventually warm our planet Earth, our home, and all the other planets that make up our solar system, each with its own unique story to tell. For millions of years, this cloud drifted quietly through space, undisturbed, a silent witness to the majestic dance of the galaxy, slowly rotating around the Milky Way's center. But beneath its calm exterior, it was full of potential energy, densely packed with the fundamental building blocks of everything that would eventually exist within our solar system. Imagine it as a cosmic recipe waiting to be prepared, all the necessary ingredients carefully measured and laid out, just waiting for the right spark to ignite the process. This immense cloud was remarkably stable, floating serenely in the inky blackness of space, a place of quiet anticipation, a cosmic pause before the symphony began. It was a time before creation as we know it, a time before the dramatic birth of stars and the formation of planets, a true cosmic dawn. The solar nebula, in a way, was our solar system's very first baby picture, a snapshot from a time long before anything we recognize existed. It was a quiet, dark, and seemingly empty expanse, but appearances can be deceiving. It was actually teeming with potential, full of gas and dust just waiting to be transformed. All it needed was a trigger, some external force, to set this incredible story in motion and begin the process of creation. The stage was meticulously set, the actors were in place, ready for something truly extraordinary to unfold. The universe, in this small corner of the galaxy, was poised to change forever, embarking on a journey that would ultimately lead to us. And it all started with a seemingly simple cloud, a cosmic genesis point from which everything else would spring. Our giant cloud was a serene and tranquil place, a cosmic reservoir of gas and dust, undisturbed for eons. It was a peaceful corner of the galaxy, a place where stars were yet to be born, until, far away in the depths of space, a nearby massive star, a giant nearing the end of its stellar life, began to undergo a dramatic transformation. When such a star, having exhausted its nuclear fuel, the very source of its radiant energy, begins to struggle, its core starts to burn its final elements. The delicate balance between outward pressure and inward gravity is disrupted. Gravity wins the tug-of-war, and the core collapses in on itself with incredible speed and force. Then, kaboom! A cataclysmic event unfolds. A supernova explodes in a spectacular display of cosmic fireworks, blasting heavy elements forged in the heart of the dying star out into the vast expanse of space. An immense amount of energy, in the form of light, radiation, and powerful shock waves, is unleashed into space, rippling outwards like waves in a pond. This explosion sent a shockwave, a powerful wave of energy and matter, racing across the galaxy at tremendous speeds. Eventually, after traveling for countless years, the shockwave slammed into our solar nebula, the very cloud that would one day give birth to our solar system. The impact compressed parts of the cloud, squeezing the gas and dust together. Imagine squeezing a sponge, forcing the water out and compacting the material. Similarly, the shockwave compressed the nebula's material, making it denser and more concentrated. This cosmic jolt, this external force, was the spark, the initial trigger. It was the catalyst that set in motion the chain of events that ultimately led to the birth of our solar system. Without that supernova, without that external push, our cloud might have continued to drift aimlessly through space forever, never igniting the process of star and planet formation. The shock wave squeezed the gas and dust together, forcing the particles closer and closer. This compression made regions dense enough for gravity, the fundamental force of attraction, to take over and begin to sculpt the cloud. It was the catalyst, the essential ingredient, the cosmic nudge that set everything in motion, initiating the gravitational collapse and the swirling dance of matter. Suddenly, the quiet cloud was alive with change, a dynamic and evolving environment where stars and planets could begin to form. The ingredients were mixed, the raw materials for a solar system were now concentrated and ready to react. The heat was on, the temperature was rising as the cloud began to collapse and compress. The process of creation had begun, the long and complex journey from a diffuse cloud to a fully formed solar system. The solar nebula was no longer just a cloud, a passive collection of gas and dust. It was the birthplace of stars and planets, a stellar nursery where new worlds would take shape. The universe had pressed start, initiating a grand cosmic experiment, and the story of our solar system, the story of our home, was underway, ready to unfold over billions of years. The shockwave squeeze made gravity take charge, pulling gas and dust inward. As the material collapsed, it began to spin, like an ice skater pulling in their arms. The more it spun, the faster it went, flattening into a disk. Most of the material spiraled into the center, forming a hot, dense ball, a protostar. This baby star grew hotter and denser, gathering mass from the surrounding cloud. When the core reached millions of degrees, nuclear fusion ignited. Hydrogen fused into helium, releasing energy. Our sun was born, bursting into light at the heart of the spinning disk. The leftover gas and dust kept spinning around the newborn star. The stage was set for planets to form. Gravity, heat, and motion were shaping a new solar system. The cosmic dance had truly begun. At the heart of it all, the sun blazed with unimaginable intensity, a young star in its prime. Its radiant energy dominated the surrounding space, setting the stage for the drama of planetary formation. A vast, flat, spinning disk of gas and dust, known as the protoplanetary disk, swirled around the newborn star. This swirling vortex was the raw material from which planets would eventually coalesce. This protoplanetary disk wasn't just a passive bystander, it was the very birthplace of planets, a cosmic nursery where worlds would take their first tentative steps. And not just planets, but also moons, asteroids, and comets, the diverse cast of characters that populate our solar system. Close to the sun, in the inner regions of this disk, it was a scorching environment. The heat was so intense that ISIS couldn't survive. Only the most resilient materials, rock and metal grains, could withstand the sun's fiery embrace. These grains, like tiny building blocks, began a slow but steady process of colliding and sticking together, driven by electrostatic forces and gentle gravitational nudges. Slowly but surely, they grew into larger and larger clumps, accumulating mass with each encounter. Through this process of accretion, these tiny specks transformed into pebbles, then rocks, then boulders, and finally the emergence of planetesimals, the seeds of planets. The biggest planetesimals, by virtue of their size, exerted a stronger gravitational pull, allowing them to grow fastest, sweeping up more and more of the surrounding material like cosmic vacuum cleaners. Over millions of years, these planetesimals engaged in a celestial dance of collisions and mergers, eventually coalescing into the 4 rocky planets that grace the inner solar system: Mercury, Venus, Earth, and Mars. These terrestrial planets, forged in the crucible of the inner solar system, are dense, made mostly of rock and metal, a testament to the harsh conditions in which they were born. Earth, our home, a vibrant blue marble suspended in the blackness of space, was born in this fiery inner region, a product of intense heat and relentless collisions. The inner solar system during this epoch was a place of intense construction, a chaotic arena where planets were built and destroyed in equal measure. Collisions and mergers, cataclysmic events on a planetary scale, shaped the worlds we know today, leaving their indelible mark on the surfaces and interiors of these rocky globes. The sun's heat and gravity, the 2 dominant forces in the solar system, sculpted the landscape of the early solar system, dictating the distribution of materials and the ultimate fate of the planets. The building of planets was a messy, often violent process, but it was also persistent, driven by the fundamental laws of physics and the relentless pull of gravity. And from this cosmic chaos, from this maelstrom of collisions and mergers, our world emerged, a testament to the power of accretion and the enduring legacy of the early solar system. Further from the sun, beyond the frost line, it was cold enough for ices to form. Here, water, ammonia, and methane froze, adding to the building materials. planetary cores in this region grew much larger, much faster. Their gravity became strong enough to capture hydrogen and helium gas. This is how the gas giants, Jupiter and Saturn, formed, with thick atmospheres of light gases. Jupiter, the largest, formed first, followed by Saturn. Even farther out, Uranus and Neptune formed as ice giants, with more ices in their interiors. The outer solar system became home to these massive worlds. The abundance of ices made all the difference. The inner planets stayed small and rocky, but the outer planets grew huge. The solar system was taking shape, with giants ruling the cold frontier. The diversity of planets was set by their distance from the sun. The cosmic blueprint was complete. Not all material became planets. Some was left behind. Between Mars and Jupiter lies the asteroid belt, a vast region of rocky leftovers. These asteroids are spread out, ranging from tiny pebbles to dwarf planet series. Jupiter's gravity prevented these pieces from forming another planet. Instead, they remain as a cosmic museum of the early solar system. The asteroid belt holds clues to our origins. By studying asteroids, scientists learn about planet formation. Some asteroids even contain water and organic compounds, the building blocks of life. The belt is a reminder of the solar system's chaotic beginnings. It's not a crowded field, but a scattered collection of ancient relics. These leftovers tell the story of what might have been. The asteroid belt is a window into the past, and it's still full of surprises. Beyond Neptune lies the Kuiper belt, a vast icy region filled with remnants from the solar system's formation. It's like a larger, colder asteroid belt, home to Pluto and other dwarf planets. The Kuiper belt holds hundreds of thousands of icy bodies and countless comets. These objects are time capsules preserving the early solar system. Even farther out is the Oort cloud, a spherical shell of icy bodies surrounding the solar system. The Oort cloud may stretch almost a light year from the sun. It's the source of long-period comets nudged inward by passing stars or galactic tides. As comets approach the sun, their ices vaporize, creating glowing tails. Studying these distant objects reveals secrets of our solar system's birth. The Kuiper belt and Oort cloud are frontiers of discovery. They remind us how much is still unknown. These icy worlds are the solar system's deep freeze, and they hold the keys to our cosmic history. Humans are explorers. We send spacecraft to study our solar system up close. Robotic missions act as our eyes and hands, gathering data from distant worlds. They take stunning images, analyze atmospheres, and reveal new mysteries. NASA's Europa Clipper will soon study Jupiter's moon Europa, searching for its hidden ocean, and maybe signs of life. Planetary defense missions like NEO Surveyor track asteroids that could threaten Earth. By finding them early, we can protect our planet. Mars rovers search for signs of past life, while probes study the sun and distant asteroids. Each mission adds to our understanding, building a bigger picture. Science and curiosity drive us to explore further. Every discovery brings new questions. Our robotic ambassadors extend humanity's reach into the cosmos. The journey of exploration never ends. The universe is waiting. From a swirling cloud to a vibrant solar system, our story spans billions of years. Earth orbits a stable star, surrounded by diverse worlds, rocky, giant, and icy. Each planet and moon tells a piece of our cosmic story. Understanding our solar system's formation helps us appreciate its uniqueness, but it also raises a profound question. Are we alone? Could life exist elsewhere? On Europa, Enceladus, or even Mars? Beyond our solar system, thousands of exoplanets orbit distant stars. The search for life is one of science's greatest adventures. Our solar system is our home and our window to the universe. Studying it teaches us about ourselves and our place in the cosmos. The story of our solar system inspires us to keep exploring and asking questions, so keep looking up. There's always more to discover.